Imagine just for a second pointing a telescope toward a planet hundreds of light years away and spotting a strange chemical anomaly in its atmosphere. An anomaly that, just maybe, could have been produced by life. It's literally one of the most profound scenarios we can even dream of in modern science. Welcome to This Explainer. Today we're taking a cinematic, scientifically rigorous look into what is essentially the ultimate cosmic detective story.
It's a monumental mystery, right? Because as of right now, Earth is our one and only known example of a living world. Honestly, we don't even have a universally accepted definition of what life itself is. So, if we can't physically travel to these distant stars to, scoop up some soil or snap a photo of alien plants, how could we possibly know that something is alive on a world we may never, ever visit?
Okay, let's dive right in. The targets of our search are called exoplanets. Basically, these are planets that orbit stars outside of our own solar system. And there are a lot of them. We're talking more than 5,800 confirmed exoplanets in our galaxy alone, but realistically, they likely number in the trillions. Now, because their distances are just so extreme, sending physical probes is completely out of the question for now. Instead, scientists are forced to rely almost exclusively on capturing light. Light is our cosmic messenger. It's really the only way we can study these distant worlds.
So that brings us to part one, the scene of the investigation, looking at habitable zones.
To solve any good mystery, you first need to secure the scene of the investigation, right? We have to start by narrowing down those trillions of possibilities to find the absolute most promising candidates. And that means looking for planets in what we call the habitable zone. This is the specific orbital distance from a star where temperatures could potentially allow liquid water to form on a surface. Not too hot, not too cold. Scientists are also looking at things like planet size, atmospheric conditions, and whether the host star itself is actually stable, rather than violently erupting and sterilizing solar flares all the time. But please, listen carefully here. Being in this zone absolutely does not prove the presence of life. Not at all. It's just a way to make the first cut. It simply makes the planet a prime suspect for further investigation.
Moving on to part two, cosmic forensics and reading the starlight.
Once we actually have a target in that habitable zone, we need to gather clues. And since we can't physically go there, we let the starlight come to us using an incredible technique called transit spectroscopy. Just imagine a planet passing directly in front of its host star. As it does that, a tiny, tiny fraction of that starlight filters right through the planet's atmosphere before traveling all the way across the galaxy to our telescopes. When that light is split into a rainbow spectrum, missing chunks of light appear kind of like a barcode. Because different gases absorb different colors of light, reading this barcode gives scientists a precise menu of the hidden gases and chemicals suspended in that alien sky.
Using this barcode technique, scientists are on the hunt for very specific atmospheric molecules. We're talking about things you're familiar with, like oxygen, carbon dioxide, methane, and water vapor. Finding just one of these is definitely exciting, but what scientists are really interested in is the combination, the abundance, and the overall context of these gases. For example, finding a mix of gases like oxygen and methane together is huge. On their own, they're fine, but together they normally react and destroy each other unless something is constantly replenishing them. Finding them together, that could be a very compelling clue.
But here is the crucial point, and we have to be incredibly careful here. Detecting oxygen, for instance, does not automatically equal life. It is so tempting for us to project our Earth bias onto other worlds and just assume, oh, oxygen, that means plants or trees. But abiotic, non-biological processes, like ultraviolet light naturally splitting water molecules apart, can easily create oxygen too. Nature is incredibly tricky like that.
Which brings us to a really vital term in our investigation, the biosignature. A biosignature is a potential sign, maybe a chemical, atmospheric, or environmental anomaly, that could indicate biological activity. It's essentially a clue that life is pushing an environment out of its normal chemical equilibrium. But remember, a potential biosignature is exactly that, potential. It is an environmental sign. It is absolutely not an automatic confirmation of aliens.
Let's look at part 3, the suspects, and why we have to be aware of false positives.
This is where we introduce the core dramatic tension of our cosmic investigation. We are up against a true master of disguise. The universe is just packed with chemical illusions, and scientists are constantly battling what we call false positives. Because what if nature can create the exact same chemical signature without life being present at all? Here's the wild thing. A dead planet can still be highly active. Abiotic or completely non-biological chemical processes, complex geological activities like underwater hydrothermal vents or volcanoes, and intense stellar radiation. All of these can generate the exact same gases that life produces. Scientists have to rigorously eliminate every single one of these alternative suspects. If they can't rule out a geological explanation, they cannot responsibly claim a biological discovery.
Now for part 4, a real case study, the JWST and exoplanet K2-18b.
To actually separate the true biosignatures from those tricky false positives, we need unparalleled power. Enter the James Webb Space Telescope. Webb observes in the infrared, which gives us this completely unprecedented sensitivity to study exoplanet atmospheres. But even with Webb, gathering this data takes a massive amount of effort, requiring hundreds of hours of observation for just a single planet. Let's look at one of its most fascinating targets, 124. That is the number of light years between Earth and a super-Earth exoplanet known as K2-18b. It's massive, nearly 9 times the mass of Earth, and it takes about 33 days to orbit its red dwarf star. But crucially, it resides right smack inside that habitable zone we talked about earlier.
When we look closely at this world, it builds an absolutely fascinating case study. Back in 2019, the Hubble Space Telescope actually detected water vapor on K2-18b. Then, James Webb turned its giant golden mirrors toward it and found carbon-bearing molecules, including methane and carbon dioxide. But the real shocker, Webb's observations revealed the possible detection of a molecule called dimethyl sulfide, or DMS. Now, on Earth, most DMS in our atmosphere is emitted by marine life, like phytoplankton. But right here, right now, I have to emphasize something strongly. These are strictly potential, possible pieces of evidence. This is not a confirmation of life. It simply makes K2-18b one of the most tantalizing mysteries in the entire galaxy.
Now, while we're out there looking for natural biosignatures like DMS or methane, scientists are also theoretically keeping an eye out for something else entirely, technosignatures. Think about it. If an exoplanet hosts not just tiny microbes, but an advanced, intelligent civilization, they might actually leave traces of their technology. We're talking about artificial radio or laser signals, or even atmospheric pollution like smog or artificial chemicals that literally do not occur naturally. But whether we're talking about biosignatures or technosignatures, they both require the exact same extreme level of scientific scrutiny.
Which leads perfectly into part 5, the verdict and the immense burden of proof.
When you're dealing with what would easily be the biggest claim in human history, the burden of proof is incredibly high. A single discovery from a single telescope on a single Tuesday is never going to be enough. We have to build immense confidence to avoid being fooled by a single observation bias. Mary Wojtek, a senior scientist for astrobiology at NASA, frames it so perfectly. She says, the presence of something that's not predicted in the environment is evidence of life. Life pushes things out of equilibrium. And because chemical complexity requires energy or enzymes to actually happen, verifying it means we need multiple independent lines of evidence. It means using different instruments, studying different wavelengths of light, and running endless laboratory models to make absolutely sure the anomaly wasn't just a telescope glitch or some bizarre alien volcano.
To manage this massive burden of proof, the astrobiology community developed what they call the ladder of life detection. It's a rigorous, step-by-step scientific progression. You start at the very bottom with a possible clue. Then, if it holds up, you classify it as a potential biosignature. Next, you have to test literally every abiotic alternative explanation. Then you demand independent observations. Then you look for multiple converging lines of evidence. Only at the very top of this ladder can you finally claim strong scientific evidence of life. Those bottom rungs are easy to reach, but much, much harder to interpret. Climbing this entire ladder requires some of the most challenging, careful measurements humanity has ever attempted. Ultimately, this whole endeavor just boils down to the purest form of the scientific process. You detect an unusual signal, you verify that the measurement is absolutely real and not just an instrument error, and then you repeat the observation over and over and over again. This strict methodology is exactly what keeps the science grounded and prevents us from falling for nature's beautiful but highly deceptive chemical illusions. So, the search for life on a distant planet is a slow, incredibly methodical climb. We aren't going to get a sudden, crystal-clear photograph of an alien city. What we are going to get is a squiggly line on a graph, a barcode of light, a subtle chemical imbalance that stubbornly refuses to be explained away by geology. And honestly, that leaves us with one final, awe-inspiring thought. Years from now, when the alternative explanations are finally exhausted, when the independent observations perfectly align, and when the data finally converges to point toward a living world, will we be ready for the answer?